Swayam Prabha. Digital India. Educated India.
This is a course on Introduction to Aerospace Propulsion. This course is intended for the students of the junior years of undergraduate program in aerospace engineering, and this course introduces the various fundamental issues and fundamental sciences related to the field of aerospace propulsion. The course will be taken by two of us. My name is Bhaskar Roy. I am in Aerospace Engineering Department of IIT Bombay. The course will be taken with me by Professor A.M. Pradeep, and he is also in Aerospace Engineering Department of IIT Bombay. And throughout this course, we will be sharing various lecture modules presented through this program. The course actually involves a number of topics, and we will be presenting these topics to you in various lecture formats. And let me give you an idea about some of the lecture formats that we will be using through the course of this particular lecture series. We will start off with Introduction to Propulsion, which I will be taking, and we will start off with a certain amount of history and the development of the science of what can be called today propulsion. When it started, it was not called propulsion, but today we call it propulsion. So, how a whole science of how to make human beings fly developed is some of the things that we will first try to look at over the history of this development. Then the concept of how the jet engines actually came about and the various formats of the jet engines that we have today. They were not there when the jet engines first appeared, and over a period of merely 50 years of development, some of those things have developed. So, we will have a look at some of those finally developed forms, and later on we will get back into the science and the technology of some of those developments.
Hello, my name is A.M. Pradeep, and I, along with Professor Bhaskar Roy, will be taking up this course on Introduction to Aerospace Propulsion. And I would be covering some aspects of the propulsion course, which I shall explain in next few minutes. We will start with basic concepts of thermodynamics. We will begin with the thermodynamic basis of propulsion devices. We will start with some introduction to basic concepts which are used in thermodynamics, scope and method of thermodynamics. We will look at why thermodynamics is used or is an important part of aerospace propulsion in itself. And then some of the other important aspects like definition of a system and boundary and surroundings, and how do you define a certain system, a thermodynamic system, which is very important for analyzing propulsion systems. We will define different equilibrium states, then the state coordinates and its parameters. We will also define what are known as extensive and intensive parameters. Subsequently, we are going to look at energy interactions, different types of energy interactions, basically classified as work and heat interactions, and as well as quasi-static and reversible processes. Followed by this, we will look at non-equilibrium and irreversible processes. So, this is where we will start with thermodynamic principles, and then we will continue with defining the laws of thermodynamics, which also play a very important role in analyzing thermodynamic systems. So, we will initially start with the zeroth law of thermodynamics, which is the governing principle for defining a temperature scale, as we shall see later on. And subsequently, we will talk about the first law of thermodynamics and its significance. Basically, as we shall see later on, first law of thermodynamics is the conservation of energy principle in some sense. And terminology that we shall come across several times in this course called internal energy, which is an outcome of the first law of thermodynamics. After the first law of thermodynamics, we shall take up the second law of thermodynamics, and very important property which we shall come across in as an outcome of the second law of thermodynamics is the entropy and the absolute temperature scale as an outcome of the second law of thermodynamics. And followed by the second law, we shall look at the third law of thermodynamics and absolute entropy. The thermodynamics of simple equilibrium, simple compressible systems, the state postulates and fundamental principles associated with that will be covered after the first, second and third law of thermodynamics. And the thermodynamic potentials and the Jacobian and Legendre transformations which lead to the Maxwell's equations will be covered subsequent to the definition of simple thermodynamic systems. The derivation of thermodynamic properties which are actually following the Maxwell's properties will be taken up subsequent to covering Maxwell's laws. And in terms of applications of thermodynamics, we shall be looking at closed and open systems, then polytropic processes and cyclic processes. And in cyclic processes, we are going to talk about different cycles of thermodynamic systems, basically power cycles, gas and vapor power cycles. We shall talk about the different types of gas and power cycles which define very fundamental power cycles which are used in engineering systems. And subsequent to the gas and power cycles, we shall discuss about mixtures of gases and vapors, and a little bit of details about one-dimensional compressible flow, isentropic flow, flow with friction and heat transfer, and normal shock flows. So, these are topics which will be covered in little bit detail as they are required for fundamental understanding of different propulsion systems. And Professor Roy is also going to cover some of the cycles that we had discussed in detail, like the Otto cycle, which is the basic thermodynamic cycle for spark ignition engines, and then the different IC engine cycles which are used for aircraft application. Then he shall also discuss about reciprocating engine performance, supercharging, and propeller speed control mechanism and gearbox. Propeller fundamentals and blade theory will also be covered in some detail by Professor Roy. And after this, I shall also take up the cycle analysis for propulsion systems, the ideal cycle analysis for propulsion systems, basically the Joule cycle and the Brayton cycle, which form the basic principle or the basic cycle for aircraft air breathing aircraft engines. Introduction to missiles and rockets is going to be covered by Professor Roy. He shall be talking about ramjets and pulse jets, and fundamental principle and working of rockets and missiles, then various space propulsive devices and their operating systems. Now, we shall now talk about the textbooks that would be used during this course. Just listing a few of them, we shall discuss more about these books in due course. For engineering thermodynamics, the book that we would refer to is the one by Professor P.K. Nag, published by Tata McGraw-Hill 2008 and 4th edition. And for classical thermodynamics, we can also refer to Emmanuel, which is an AIAA educational series book. For propulsion course, we would be referring to the book by Hill and Peterson, Mechanics and Thermodynamics of Propulsion, and the other book that we should also refer to is the book by Professor Roy himself on aircraft propulsion. There is also a book by Mattingly on elements of propulsion, gas turbines and rockets, which is an AIAA education series. And we shall be mentioning about more reference material as we during the progress of the lecture series.
Let us first get ourselves introduced to some of the basic sciences that are involved in the field of propulsion, what we call today propulsion. Fundamentally, we are talking about motion of aircraft and spacecraft. Hence, the first thing we would need to really be concerned ourselves and knowledgeable about are the laws of motion, because motion is what we are going to really bother about over this entire course of propulsion, how to create motion. That is our concern in this course. As Professor Pradeep has introduced to you, the next thing that we would need to know quite a lot about are the laws of thermodynamics, because the creation of motion and the field of propulsion is based conceptually on the field of thermodynamics. Thermodynamics forms the backdrop on which the entire field of propulsion has been created. Essentially, thermodynamics is the matrix on which the field of propulsion has been created on. So, we need to know quite a lot about the thermodynamics, which Professor Pradeep will be covering in his lectures over this lecture series. And then he will also cover a little bit of principles and theories of aerodynamics, which we need to know. Much of the propulsion that we will be talking about essentially concern a lot of aerodynamics. We would need to know many of the aerodynamic laws, the aerodynamic principles, the various aerodynamic mathematics that is required. And in many of the modules that we will see that the various components of propulsion or propulsive devices essentially work on the principles of aerodynamics, and many of them are indeed actually called aerodynamic machines. So, we would need to know thermodynamics, we would need to know aerodynamics, and you would see later on that many of the propulsive devices are indeed actually referred to as aerothermodynamic devices. So, we would need to know both these sciences quite well. Then we would need to really be involved ourselves with the various aspects of the mechanical issues, the mechanical sciences. There is a lots of mechanical engineering involved in making propulsive devices, engines, which basically are mechanical entities, and we would need to know some of the mechanical sciences without going very deep in this course into the mechanical engineering, but we would need to know one or two things that surely as basic mechanical engineering background we would need to know. There are issues involved about the material sciences, the metallurgical sciences, many of which actually are required in building the propulsive devices. The propulsive devices often use the material science and metallurgy of the highest order. The cutting edge of the material science and metallurgy are often used for the propulsive devices. We would time to time have a look at them without really getting deeply involved in the business of material science or metallurgy, because strictly speaking that is not really our focus here, but we will mention them as and when they are required to be mentioned. And then there is a question of controls. Most of the devices that we need to have, the engines or the propulsive devices that run an aircraft, that fly an aircraft, the propulsive devices that fly a rocket or a spacecraft need to be controlled. These control theories are extremely involved. They are sciences by themselves, very deep into them. We would not be able to go. Once in a while, we will mention some of these control issues just to keep you abreast of the situation that some of the propulsive devices do need to be associated or embedded with modern control theories and control systems. Let us start with what we call motion. What we are trying to create is a propulsive device that will aid an aircraft or a spacecraft going through motion, which we would like to call continuous motion. It is not just a motion for a few seconds or a split second, it is a continuous motion that we are talking about, and hence there is a requirement that these motion be subject to certain fundamental sciences which govern the motion of various bodies. We know that Newton's laws of motion actually codified the various concepts of motion, and these motions are what we would certainly be most concerned about in this course. However, even before the Newton's laws of motions actually came into being, the concept of creating motion through various kinds of instinctive understanding of motion were actually applied. For example, paddling of oars to make the boats move in water uses the laws of motion instinctively without quite knowing the laws of motion, and that has been going on for thousands of years. So, the question of using the motion has been kind of in the instinct of human beings or in the human civilization for thousands of years, really speaking, and Newton or Isaac Newton actually codified those laws in the form of physics and mathematics, and making it easy for us to create propulsive devices using all the sciences and engineering. So, let us look at a few motions that people have been talking about. One of the things, for example, people mentioned or came up with, can we create perpetual motion? And I think it is pretty much now understood that perpetual motion is, strictly speaking, not physically possible. This has been possible due to the various laws of physics and mathematics that has come into being, and they have clearly proved that it is not really possible to create perpetual motion, which means that we have to have devices that create motion on a continuous basis. You cannot start a motion and sustain it for a long time on a perpetual basis. You have to create a device that on a continuous basis aids the process of motion, and in our case it is a process of flying motion. And this continuous application of force or power is what finally we need to provide through the propulsive devices. So, our job here in this course is to see whether the continuous application of force and power can be provided for continuous flying motion. That is our concern in this course. Let us go through a few stories. I will tell you a few stories to begin with, how the motion or a flying motion and making power or force to create motion started developing in human civilization. More than 2000 years back, something called aeropile was created by a gentleman called Giovanni Hero in 2nd century BC, and he demonstrated a particular device in which if you put a steam and allow the steam to come out through jets in opposite direction, you could create continuous motion of a ball. This ball could be held through on two sides, and you could have continuous rolling of the ball, and he at that time it was called aeropile in Latin. After nearly 1800 years or so, or nearly 2000 years really, William Avery actually created this ball, and the picture that you have on the right side actually is a picture of the Hero's aeropile created by William Avery 2000 years after Hero conceptualized this motion in actual physics. Now, remember those days in the time of Hero, there were no Newton's laws available to him. So, he built it on his understanding of motion, and then William Avery created that 2000 years after that concept was created. And then somewhere around 13th century, the Chinese scholar Wan Hu decided to try and create a flying motion. Now, we all know that China is very good in creating gunpowders and fireworks. So, they had the concept of making small rockets through which more of fireworks and things could be made to fly. What one who as a scholar thought could be done is, if you put in a number of rockets and fire them up together, he could make it fly an object. So, what he did, he created a chair and he put a number of rockets under the chair, and he went and sat on it himself. And he had his assistants who could light up those rockets and simultaneously, and once those rockets were lit up, he is supposed to have flown up. We do not have a quite story actually what happened to him, but it seems it was one of the first attempts to make human being go up in the air, and that was in 13th century AD. It happened. It reportedly happened in China. It is a story, we do not know whether it actually happened. The picture you see is a picture created by an artist. And then of course, we have Leonardo da Vinci. Now, he is of course the genius of the millennium, and few things that he created we discuss even today. So, in somewhere around 16th century, he created what is now known as chimney jack, in which the hot air from the chimney, when it is rising up, creates a motion or of a turbine, and this rotating turbine then he used to rotate a number of elements using gearbox and belt and pulley drive to finally create motion. So, he used the hot gas of a chimney to make a turbine. Now, conceptually, that was one of the first attempts to create turbine through moving of the hot air or hot gas. Of course, subsequent to that or around that time, in many places over the world, wind turbines were being created, which uses the natural air or wind available in the atmosphere. Da Vinci created a machine using this within a small space inside a chimney. However, the more abiding contribution of Leonardo da Vinci is what is known as ornithopter. Ornithopter was created by him as a means of actually making human beings fly. His idea was that you can create a small platform which a human being can sit or lie down, and then it would have something like a helicopter, what we call helicopter today, which will have a vertical motion. It is something like a screw motion, and the whole device would rise up in the air using kind of a screw motion through the air, and it will move up. This was his concept of an ornithopter, which of course, he never actually made. He only conceptualized the whole machine. It never was actually made by him. Da Vinci also created what is known today as the flapping wing concept. Now, flapping wing, of course, you can well imagine is a copy of the birds flying, motion of the birds flying. This is what Da Vinci thought, that if we could imitate the mechanical motion of a flying bird, we should be able to make human beings fly like birds. He noticed, as an avid scientist and an engineer, that flapping wing contributes to the flying motion of the birds. So, he created a small machine, a conceptual machine, in which he thought we could have flapping wings, and if those could be actually flapped during the process of flying, it would aid the motion of this particular craft. This is what he had in his design. I am not sure he ever made them actually, or whether anybody actually made them, but as a concept, there was nothing wrong with it. And today a lot of people are actually talking about flapping wing concept as one of the modern aids of making new aircraft, small aircraft maybe, with flapping wing concept. The problem of course was not just making an aircraft, powering the aircraft. And to power an aircraft, it is necessary to have engines. So, when we talk about propulsive devices, we are talking about devices that has an embedded engine inside it. Now, this engine works often on the principle of thermodynamics, as we have seen, but the mechanical sciences that do come in the process of this propulsive devices involve a number of elements. Let us look at some of these elements. Now, nearly 400 years back, a gentleman called Branca came up with the idea of a jet turbine. Now, in those days creating steam was a known thing. So, if you boil a large beaker and create steam and then allow that steam to come through like a jet and impinge on a turbine which is rotated, which is held in a shaft, a vertical shaft, it would create a rotary motion. This rotary motion could be transferred through the gears to a shaft, and then this shaft can be then used to run a propeller. So, the entire device is essentially geared towards creating a rotary motion, and this rotary motion would finally be running a propeller, and that is this propeller which would then make an aircraft or a craft to fly through the air. That was the concept. So, at this particular time, the people were more bothered about creating an engine in which the propeller could be powered, could be supplied with continuous power, so that the propeller would create continuous propulsive force, which in turn would aid a craft to fly on a continuous basis. So, this was the idea with which people like Branca started creating devices in which continuous motion could be generated. And then came Isaac Newton's concept of steam wagon. He created this particular sketch, in which his concept was that if you just create a steam jet out of a big large beaker or something, you heat it up from the bottom with some heating aid, and then the steam that comes out, if it is made to come out through some kind of a nozzle, and the steam jet would aid the process of movement of a wagon, and it was called Newton's steam wagon. This was just a sketch, this was never made, and we are not quite sure this would actually work, because the amount of force required to move a wagon would have probably been impossible to create through some such steam wagon. However, as a sketch and as a concept, it provided certain ideas to people who came down the line, and we will be talking about the Newton's laws of motions in a few minutes from now. And then of course, the whole idea of creating steam and using the steams to create various kinds of continuous motion was followed up by a gentleman called Barber, and he created a steam driven compressor turbine, and this he is supposed to be a precursor to what we call today jet propulsion. This is nearly 200 years back, little more than 200 years back, and the whole contraption he had created in his own backyard with the help of what was at that time known as chain and pulley system, and as a result of which this contraption was probably one of the first in which a kind of engineering was used along with the concept of steam force to create what can be called continuous power generating unit. And then of course, came the Newton's laws of motion. Now, many of these laws today form the basis on which various kinds of bodies move, whether it is aircraft or automobile or any other body that moves on earth, essentially follows the Newton's laws of motion. In fact, they have to conform to the laws of motion, and when these crafts are created, it is essential at the time of creation they are made to conform to the laws of motion. Let us first quickly try to understand these laws of motion. The first law, which states that object at rest will remain at rest unless acted on by an external force. An object in motion continues in motion with the same speed and in the same direction unless acted upon by an external force. Now, this law is often called a law of inertia. That means, a body maintains its state of inertia. The state could be the rest or it could be a state of motion, and it will continue in the state of rest or motion as per this law of inertia unless and until it is acted upon by an external force. This external force need to be applied. This is essential to understand that to create continuous motion of any craft, and indeed an aircraft or any spacecraft, you need to create continuous external force. You need to continuously provide force or power to aid the continuous motion. This is the important first thing that people need to understand, that if you do not have continuous source of power and continuous propulsive force, you cannot have continuous motion, whether in air or anywhere else. This establishes the law of inertia as we know today within the Newtonian frame of reference, which means that the bodies we are talking about are Newtonian bodies, the motion we are talking about are called Newtonian motion. We have to understand this from the point of view that some of the concepts here may not be exactly accurate if you bring in the modern theory of relativity. In theory of relativity, the state of motion and the state of rest are defined slightly differently. So, the Newtonian motion is what we will be bothered about, we will be concerned with, and we will not concern ourselves with the theory of relativity at any point of our discourse in this lecture series. Even when we talk about the spacecraft, we will never be talking about the motion of a body in which the relativity as a law of physics comes into the picture. So, we will always be in the Newtonian frame of reference. Let us look at the Newton's second law of motion, which states that acceleration is produced when the force acts on a mass. The greater the mass of the object that is under consideration, which needs to be accelerated, the greater the amount of force needed to accelerate or create the motion. Creation of the motion itself is a kind of acceleration. When you are starting from a state of rest, you need force, and that itself is the first acceleration that you need to produce. It is codified simply as F equal to m into a, m being the mass which we would call the rest mass. And as I was stating, in theory of relativity, the definition of the rest mass is different from what we would consider in the Newtonian reference. So, this mass to be accelerated requires a force, and this is what the second law states, and our business in propulsion is to create this force, so that motion can be created. The third law of Newton's motion, as is codified, is every action has an equal and opposite reaction. Now, this is probably very well known, or one of the most well known of all the laws, and this is the one of the main laws on which the propulsive system that we will be discussing is based on. Actually, the propulsive system that we will be talking about are based on all the laws, not only the third law, but people talk about the third law as the more important one. We shall see that all the laws are really speaking almost as important as the third law in creating the propulsive devices. Now, this states that if you create an action, there is bound to be an equal and opposite reaction, and as the diagram illustrates, that if an action is created to push a body, if a certain amount of material is ejected from a body from the rear, as the diagram illustrates, the act of releasing of that amount of material from the rear is the action. The reaction is the force that propels the body forward. Now, this is the concept on which most of the aircraft and spacecraft motion is actually based on. So, this action of creating a release of certain amount of material from the rear of a body which we want to move is the first principle on which the propulsive devices are created on. So, Newton's third law does create one of the bases on which basic propulsive devices have been created. This was generated conceptually long back. If you fill up a balloon and let us say you hold the balloon in one hand, and then if you, for example, release take your hand off and allow the pressured air, compressed air stored inside the balloon to suddenly come out through that open lip, it will create a nozzle, as we saw in the illustration of the third law. Now, this nozzle effect immediately creates a reaction. So, the action created by the release of the air from inside through that open lip creates the force, and that has a reaction. That reaction makes the balloon move forward. If you do that yourself in a room, you will probably find, release the balloon actually, you will probably find the balloon moving in a zigzag motion. It is not because anything has gone wrong with the balloon or anything has gone wrong with your release of the balloon. The point is, the balloon is always moving as a reaction to the action instantaneously through that lip. So, the instantaneous reaction direction or the magnitude and direction actually creates the instantaneous motion of the balloon. So, the zigzag motion that you see is the correct motion depending on the instantaneous vector of the action that is created, and reaction is nothing but opposite to that particular vector. Now, this is then shown in the lower diagram, which actually tells you that in an aircraft, flying aircraft for example, if you create an action which throws something towards the back, and this something we shall see more and more is actually the air in which the aircraft actually is supposed to be flying. If you create this action of throwing the air backwards, then the aircraft actually experience the reaction, which is the motion forward. So, our business in this propulsion course is to see how this action can be created through various devices on a continuous basis in a controlled manner, so that in a controlled manner you have the reaction and the motion of the aircraft. We cannot allow the aircraft to move in a zigzag manner as we see in the balloon. We have to have a continuous controlled smooth motion of the aircraft, and this smooth motion of the aircraft needs to be done in a controlled manner. This controlled action and reaction needs to be created through propulsive devices, and there is a question of integration of the propulsive device with the aircraft, and we shall be talking about some of these issues more and more as we get into the subject matter. Let us get back into the Newton's first law a little more in detail, because that is what is going to create the bedrock for our subject. This law states that if the vector sum of all the forces acting on an object is 0, then the velocity of the object is constant, which means that if it is in a state of rest, it will remain in a state of rest. If it is in a state of motion, it will remain in a state of motion without experiencing any change in its motion. There will be no acceleration, there will be no change in velocity, there will be no change in direction. If you want any of those three, a change of direction, an acceleration or a change of velocity, you would need to apply force, and this force need to be applied, as we saw, in a certain direction. So, the vector sum of all the forces is what we need to have our eyes on, so that the motion can be created in a particular direction, in a particular, giving it a particular magnitude. So, creation of motion as per the Newton's law is the first thing, giving it a direction is the second thing. We need to keep our eyes on both the issues, that is, creating the motion, the magnitude of the force that need to be applied, and the direction in which the force need to be applied, because the reaction will be based on both the magnitude and the direction of the action that is created. Reaction will be opposite to that magnitude and direction. Then we look at the Newton's second law of motion. The second law states that the net force on a body is equal to the time rate of change of its linear momentum, which let us call capital M subscript t, in a specified reference frame for the internal inertial motion under our interest. I have stated that we are talking about Newton's reference frame, and we called it the inertial motion, and that is codified in simple mathematical formulation as F equal to d mt dt. Now, this mt is the momentum, and in our case it is a linear momentum that we are talking about in a particular direction. The direction is important, and this can be now stated as m v, m being the mass, v is the velocity, the instantaneous velocity, and we are considering m as the rest mass. This is the change in the momentum, which can also be written down if we consider the rest mass is constant. That means, the mass that is activated on, if it is considered a constant mass, then if we can take it out, and what we have is m into dv dt. Now, this constitutes what we call the acceleration, and mass into acceleration is what we had written down earlier, and we will be bothering about considering the fact that we have a certain amount of mass or to play around with, to act upon, and on that mass, on that given mass, we will have to create a certain amount of acceleration of dv dt, which will then create a change of momentum, which creates the force of action, and then that will be reacted upon to create the motion of the aircraft. So, any mass that is gained or lost by the system will cause a change in momentum. That is not the result of an external force. A difference equation is necessary for a variable mass system. Now, this is the issue that one needs to keep in mind, that the mass that we are talking about in the earlier equation, for example, we considered finally that it is a constant mass system. If we have a variable mass system, which is perfectly possible, for example, in a spacecraft, when the mass stored in a spacecraft is used, and over a certain period of time that mass is used up, and towards the end the amount of mass flow that is available could actually be a variable mass, in which case the equation that we would need to concern ourselves with from the Newton's second law would start looking slightly different. So, we need to keep an eye on the fact that for most of the time we will be considering ourselves with a constant mass system, but if we have a variable mass system, we would need to come back here and apply necessary correction. Now, consistent with the first law, the time derivative of the momentum is non-zero when the momentum changes direction, even if there is no change in magnitude. Now, this is what happens when you have a circular motion. That means the instantaneous velocity of the motion is always constant, but it is continuously changing its direction. This change of direction also requires an external application of force, and this is what we would need to do. Let us say when an aircraft is taking a turn or a spacecraft is taking a turn of its flight, which may be circular, which may not be circular, but to effect that change of direction you would need to have applied forces. So, the propulsive devices should be able to create that change in the direction of its action, so that the reaction force which makes the craft move can also create the necessary change in direction of the craft. The relationship also implies that we have conservation of momentum. When the net force on the body is 0, the momentum of the body is constant, which could be 0 or non-zero, and the net force therefore is equal to the rate of change of the momentum, assuming there are no loss of energy anywhere. This is the principle, fundamental principle on which the action reaction actually works. So, this is what we will be starting off with when we create the propulsive devices. Newton's second law is the conceptual basis of the propulsive force of all the flying vehicles. We shall see more and more that popularly Newton's third law is mentioned as the law that creates the propulsive action, but we shall see more and more that Newton's second law is what actually is activated or used more inside the propulsive device to create all the motions and all the basic physics that are required in the process of creating the propulsive force. At very high speeds, as I mentioned before, the approximation that momentum is the product of rest mass and velocity is not accurate, and hence the theory of relativity, which we are talking about the motion where near the speed of light. Okay. Those are the motion we are not going to be concerned with in our various devices that we will be talking about, and we will restrict ourselves to the propulsive purposes that use the Newtonian laws concerning the Newtonian bodies, the Newtonian fluid, and finally, the Newton's motion and the Newtonian motion that we will be restricting ourselves to. Impulse is a corollary of the impulse, the force that we are talking about. The impulse I that is defined here is a force acts over a very small interval of time, and it is defined as I equal to integral of f into dt. Now, this is the concept which is normally used or often used to define the impulsive force that is required, or often defined as the force that makes rockets, space vehicles and missiles move through the air or in the space. And we shall come back to this concept of impulse when we deal with the rockets or space vehicles later on in this course. And now, we come to the Newton's third law, which as states that all forces are interaction between the different bodies, and then as a result of which there is no such thing as a unidirectional force or a force that acts only on one body. The law states that every force has a counter force, every action has a reaction. So, there is nothing like an action and the end of the concept. Every action has a reaction. The moment the action is created, we have to consider the fact that the reaction is there, and as a result of which is the reaction that we would actually be more concerned with, because the reaction makes the craft actually move. So, if we put it this way, if a body exerts, body A exerts a force on body B, the body B simultaneously exerts a force on the same magnitude on the body A, and both the forces are acting along the same direction, along the same line. This is the fundamental issue, that we have to create action, and that is not the end of the story. We have to bother about what happens to the reaction. In the next class, we will have a look at some of the devices that people have been trying to create using some of these laws of physics and laws of mathematics and laws of understanding of the engineering, and some of the devices that were already in action at that point of time. And we will have a look at some of the devices that people have been creating over little more than 100 years. And these devices, many of these devices were patented, many of these devices were actually created and tested in the laboratory, and where some of them were found to be quite useful. And we shall see that some of them actually, even though they were great devices to begin with, they had some shortcomings, because of which we may not be using them today. So, we will look at many of these devices, and we will look at some of the history of the development of the aircraft and spacecraft, and how the propulsive devices, the engines that make these crafts move, actually have developed over a period of nearly 150 years. We will start from even before the Wright brothers. We will look at people who have created the devices. We will look at the Wright brothers plane. We will look at many of the engines that Wright brothers and others actually used in the process of creating flying crafts. And then we will see what is the state of art as of today in the field of aerospace propulsion.